So I think in the first Hansen session, we discussed about only two types of data set. Basically, sorry, two types of set, right? Which can be derived from a data set, given data set, which is train set and test set. So now you might have heard about there is something called as a validation set. So can you please tell me why do we need validation set and what is exactly a validation set? You can write your answer in the chat box. I just want to see whether you know the validation, I mean the meaning of validation or not. And is it really required for us? Yes. So you can write in the chat box. Have you ever used validation set? What is the use of a validation set? And how to get a validation set given a data set? Yeah, am I audible? Am I audible? Maybe there is some issue from my end. I could not able to see the chat box. Yeah, क्या स्टार्ट हुआ गया क्या? मैंने स्टार्ट तो कर दिया. Okay, but
यूट्यूब पे हाँ हाँ सर ये आप कुछ नहीं हो रहा मतलब म्यूट हो गए आप यहाँ से ऐसा कुछ दिखा रहा है यहाँ तो चल रहा है सब कुछ हाँ एक बार वापस आप लॉगिन कर लीजिए रीचेक कर लीजिए स्टार्ट किया
yeah. So to check the performance of a model on a validation set, which part of the initial training set only? Okay. Any other answer from the participant side? That have you ever used validation set to train the model, or what is the need of it? I could see some answers. If an image dataset has 1000 images, then 700 images can be used for training, 300 for testing, and a validation set can be obtained from the 700 training images. Okay. Before final development of a model, we check the performance. Yes, final deployment, we check the performance of a model on the validation set. Validation set is a proportion of the initial training set only. Yeah, the answer is absolutely correct. This validation set is also helps us in overcoming some of the problems, right? I mean, whether the model is a is suffering from underfitting problem or overfitting problem, and you might have also heard about something called as a bias. So I've shared my screen. Okay, I think my screen is visible. Yes, is it visible? Okay, okay, thank you. So as I mentioned earlier that if a data set is given to us, right, having, let's say, I mean, let us consider the same example, right, which we have taken in the last class, that we are having, let's say, for example, 1,000 number of, 1,000 number of images, let's say, for example, we are given 1,000 number of images, and we have applied, let's say, for example, I'm choosing 70% for training and 30% for, let's say, for example, right, testing, and there are two classes. Let's say I'm choosing a situation where there are, let's say, for example, 600 samples that belong to one class, 400 samples that belong to another class. Let's say this is normal, this is abnormal, and you are solving a problem. And of course, if you take 70%, so there will be 700 images in the training set, and there are like 300 samples in the test set. And what we discussed earlier, that yes, this training set, the samples of the training set will be helpful in designing the model. I mean, basically to train the model. And once the training is complete, I mean, the training is successfully done, so you can just check the effectiveness of the model on the test set, that how it is performing on the unknown or on the unseen data, because we haven't passed this testing set, right, during training. So we'll be having both X and Y, that means both input and output, and we will pass this to the model. We're only talking about the supervised learning scenario, where we are passing the input image as well as the output image together, right? And where, let's say, I varies from 1 to 700, 1 to 700, right? So this Xi is nothing but the image, and the YI is the corresponding label. That's what we are sending. I mean, based on this, we are designing a model. I mean, this model can be any model, right? Can be a neural network based model, can be a convolutional neural network based model, and then ultimately what we are getting is a trained model. And then on the trained model, we are just applying, or you can say, these 300 samples from the test set and checking the results, whether the classification results, right, which we have obtained are correct or wrong. I mean, whether the classifications are correctly classified or misclassified or like that. That's what we're doing. So now then, what is the need of this validation set? Now this is what is the question here, right? Okay. So then how would you know? Let's say you don't have any idea about this validation set. So now how would you know that your model is suffering from underfitting or undertraining problem, right? There are two problems which are very, very crucial. So if your model is not performing well, then it is either due to underfitting or mostly, right? I mean, in general, I'm talking about, or overfitting. So what is this scenario? Underfitting and overfitting. So let me just tell the answers because we don't have much time. So underfitting, and how do you know that your model is suffering from overfitting issues? If your model is performing well on the training set, okay. So training accuracy, let's say for example, is good, right? And the testing performance is not good, right? So that means overfitting is that scenario where you found that your model has been trained perfectly. It is giving very good performance during training, but during testing, my model is not going to perform well, right? So that means, I mean, the generalization performance of this model is not good. That means the model is having poor generalization capability. It is performing well on the training data, but not performing well on the testing data. So in the underfitting is such a scenario where your model is not performing well on the training data, right? So training accuracy is also not good. So if the training is not good, so of course the testing performance also is not good. So that means, so this is how actually you would get to know about whether your model is performing well or not. So your training performance, if your training performance is not good, so you cannot expect a good testing performance from the model. And this type of scenario is an underfitting scenario. That means you have to train the model, right? I mean, more time, right? I mean, for more number of epochs, you can say, right? So that means so that the training accuracy or the training error is, is less. It should be very, very less or close to zero. And you have stopped the training just before even the best point, you can say. So similarly, coming to the overfitting issue, and this can be easily handled, right? Underfitting issues can be easily handled just by training the model for more number of epochs like that. But this scenario, this overfitting scenario, is very, very dangerous. So what it tells, right? The training performance is very good. So that means the student was doing very, good at solving the problems, or maybe, solving the problems along with the teacher, right, in the classroom, but the testing performance was not good. So this type of scenario is known as overtraining and overfitting. How to avoid this type of problem, right? And the simplest way is to use something called as concept early stopping. What do you mean by this? You have to stop the training process. You have to stop the training at some amount of time. So for that, what we need is something called as a validation set. And this validation is nothing like a kind of class test for us. So we will train the student till his performance in the class test is good, right? If the performance of the class test is starting degraded, then we have to stop the training process, right? That means the student is going to be overloaded. That is very, very easy to understand. So if you train the model, more and more, right, for more number of epochs, the training performance is going to be very, very. This is a training error. The training call. Maybe the number of epochs or the model complexity, you can say. Right. So the more you train, right, you will get less training error, but when it is applied on the test set, so what happens? There's a possibility that the performance of the model, right, may start, degrading. So if you just look at the performance of the validation set, it is a kind of test set which can be easily derived from the train set, and we'll talk about it, how to derive it, right? So what I'm trying to say here is that every time during training we need to check the validation performance. So there can be some point where the validation error starts increasing instead of decreasing. and we have to stop the training process here. So this is why the name is so-called early stopping. So this is where you have to stop the training process. You should not go beyond this point to further train the model, because what we know that if you further train the model is going to be complex, right? So that means there is a possibility that the validation error starts increasing, and if the validation error starts increasing, there's a high possibility that the test error is going to be also high. So that is why it is better to stop the training here. So that is also very, very important, that way to stop the training process. How would I know? And this is known as early stopping, the simplest way to overcome the overfitting issue. And that is why we need a validation set most of the time. Right? And now the question is how to derive this validation set from the set. Test set is something very different. It's something very, very different. Right? We should not touch the test set. It should be kept separate. Right? Because this test set is only used to evaluate the model. So what we have is only the training set, and validation is again, right, just to when we are building a model, that is where we need the validation set, right? That is all about the part of the training process. So like one response I have seen in the chat box, right, by Pooja Soni, right, that we can easily obtain the validation set from the training images. Now the question is, how would I get this validation set, let's say from the 700 training images? Is there any procedures, how to? Is there any procedures, Okay, there are a lot of things. For hyperparameter tuning, yes, of course. Validation set is, of course, right. That is what is model complexity. When I say it is like the model can have a lot of parameters and a lot of hyperparameters. So based on what hyperparameters, you can also use the validation set for this. Absolutely true. I mean, you can also tune the hyperparameters based on the validation set. Absolutely true. To check the learning process, that is what is we are talking about. I mean, whether the learning is what kind of learning we are having, right? I mean, whether the performance is good on the training set as well as the validation set or not. Yeah, we can divide the data set into 3 parts: train, test, validation. Sometimes if you are lucky, then you will get the data sets already separated. That means training, testing, validations are already given to you. And most of the standard data sets, they usually provides official split, or they used to provide the folders, right? Basically 3 folders: validation, test, and training set. Then nothing to worry about it. How to divide the data set? Let's say, for example, you have collected the data set by yourself, and your task is to divide the data set into 3 parts, right? So how would you just do that? Is there any, yeah, again use 70-30. Okay, I mean, either you can use 70-30 or you can also use 80-20, right? No worries. I mean, you can use anything. And I can also see other, responses. Yeah, cross validation. Yeah, absolutely true. K-fold cross validations. We can also, use cross. These are the 2 popular techniques, which are basically used to further divide this training set into 2 parts, like into. If you want, you can again use 70-30 or 80-20. It's up to you, right? So how much percentage you want to give it to only training set or only validation set? So you can finally get the final training set over here. So this is the final, the final training set, right? And this is the validation set. So in place of this, you can also use K-fold cross validation, right? And again, the stratified concept has to be there in all the cases, right? Whether it is percentage split, whether it is K-fold cross validation, please remember the concept stratified, which we discussed in our previous class, right? Stratified. The proportion in a particular fold also. Let's say you are choosing 5-fold, cross validation. So you have to divide the 700 images into 5 number of folds. You know that fold 1, fold 2, fold 3, fold 4. fold 5, and you have to repeat the procedure for 5 times, right? And you can consider just one as a validation set and rest 4 as a training set. Similarly, the second one, and you have to do independent training, right? So you should not choose the same, you should not choose the same model which was already trained on this. So, I mean, I've seen this type of mistakes, my students did, and they used to say, sir, I've got, almost 100% of answers. I mean, they are using, the same set of model which was adopted in the first, you can say here in the first cycle, or you can say the first run, right? In the first run, if you are choosing the fifth set or the fifth fold as a validation and rest 4 as a training. So in the second case, or in the second run, this is for run 2. So you can choose this as a validation and rest 4 as this. And you have to train these models independently, right? You should not retrain the model which is already trained on this, because the model has already seen this last, I mean, basically the validation set, and which was earlier fold number 5. And now you are considering that as, fourth, which was earlier used for training. So you will get 100% results for rest 4 cases, right? Because the model has already seen all rest 4 cases. So you should not do this. Right. So these are some of the things which you need to keep in your mind, and while dividing the data set into training, testing, and validation, and then you can just start designing your convolutional neural network model. I think you still remember, I mean, the kind of CAD systems which we designed using machine learning, where we first divide the data set into 3 different parts or 2 different parts, and then once you are having train set and validation set and test set, right? Then you are ready, and now you can just use these 2 different sets, right? Validation set and train set, to train a CNN model, right? Now you can design a model, CNN model, you can train the CNN model, right? And ultimately you will also get some of the probability values at the end using this softmax layer. If you're solving a classification problem using a softmax layer, you will get the probability values. Let's say you are solving a 10 class classification problem, you will get 10 different probability values. And as I mentioned, that if you're solving a classification problem, you have to initially process the output level like 1, 2, 3 up to 10 into its corresponding 1 hot encoding. Like 1 has to be represented in this way, 2 has to be represented in this way, 3 has to be represented 0, 0, 1, 0, 0, 0, like that. The last 10th class will be represented as 0, 0, 0, 1. So now you will get again a probability value, 10 set of probability values here. This is a 1 probability distribution. This is another probability distribution. And then you have to find out the cross entropy, basically the categorical cross entropy we discussed, right? Same procedure you have to follow. Instead of converting the image into a vector to process through the traditional neural network, we are directly passing the images to the convolutional neural network, and it is the job of the convolutional neural network model to train, basically to optimize the parameters, or you can say the coefficient values of the filters, right, which is required for us. And here in this case, we are learning the features rather than extracting the features from the images, and that's why these are known as sometimes end-to-end learnable, because this is very, very important for us. And these are not handcrafted, these are non-handcrafted features, right? So because we are learning the features as well as the classifiers over here, right? So we are learning everything here, right? So we are extracting the features by providing the filter values randomly. These are filters, the filter values are applied over the images, and we don't know whether these random values are important for us or not, or whether these random values are helping us in extracting meaningful features from or not. And that's why we are updating the features, right? So we need to update the features in such a way that this X, for X, whatever we are getting Y cap has to be similar to Y, right? And that is why it is working, right? And the number of layers and all, right? So that's up to you, that how many layers and why there is a need of deeper number of layers or not, right? We discussed. This is, you can say the assignment number 1, where we have to design a CNN model and design The final layer, or we have to also provide the number of neurons need to be, the number of neurons that should present in the final layer, and what kind of activation function we should use in the final layer for classification problem, and what kind of, you can say, what kind of activation function and what kind of loss function as well. So at the same time, you have to also provide the optimizer. These are all the important hyperparameters, right? Optimizer, you know how important it is. It can be SGD, it can be RMS prop, it can be ADA delta, it can be ADAM, which is the most popular one, and the latest one is ADAM W, right? So you can just use any one of them and you can check. So optimizer is one of the important hyperparameter we have. Similarly, learning rate. We all know the importance of the learning rate in the from the gradient descent rule, where the new weight can be written as the world weight minus eta into del J is the loss function, let's say L, right, upon del W. So that is what is eta, and this is very very important. The value always lies from 0 to 1. So but we cannot take that theta value close to 1, which will be very very faster, because this eta is helping us, is a kind of known as learning rate, sometimes learning step size also we can say. So we need to be very very careful while choosing eta value, and this eta value can also be adaptive, right? You can also choose some adaptive approach, right? This is the best approach to choose the eta value. So similarly, you can decide the number of epochs you need to run, that you need to also decide the batch size, right? Which is very, very important. If you are dealing with, let's say, classification problem or segmentation problem, if you are having, a good amount of GPU available in your system, then you can just choose the higher batch size, or else you have to choose a smaller batch size, right? It is just, we have talked about, we are just following here batch learning process or batch learning strategies, or sorry, basically mini batch learning size, right? So for every batch, you are computing the error, and you are just repeating the same process, right? So those are known as the number of iterations, right, per epoch. How many batches are required to complete the full epoch. So that those are known as iterations simply here. So these are some of the important actually factors, you can say the hyperparameters which you need to decide by yourself, right? So hyperparameter tuning is one of the major concern while designing the convolutional neural network. It's not like you have designed a convolutional neural network, but if you have not chosen, let's say, the hyperparameters carefully, so probably you may not get the expected result whatever you are planning with. So that's why hyperparameter tuning is very very important, right? Along with the design of the convolutional neural network, both plays a very very important role here. And coming to, I will also show you the corresponding code. I'll demonstrate. And the second case which we discussed is like transport learning, right? So transport learning is very, very easy, as I mentioned earlier. So what we need to do is, let's say the AlexNet is already there, or let's say VGGNet. Let us consider VGGNet is the architecture which is already available with us, right? So let's say this is the whole VGGNet architecture, having a lot of layers, and finally it ends up with three layers, three dense or fully connected layers, having 4096 neurons, 4096 neurons, and 1000 neurons. And this is a pre-trained architecture and has been trained on ImageNet dataset, having 1000 classes. And all of these, images are natural images here. Fine. And now you want to solve a medical imaging problem. You need to choose a medical imaging problem, and you want to solve this VGG. You want to solve your problem with the help of VGG network. So how to do this? Let's say your task is a 5-class classification problem. Fine. So as I told, already that you have to first replace the last layer. So this layer has to be initially replaced, and with a new layer, this layer has to be replaced with a new layer, which is having only 5 neurons. So these connections are new for us. Like these connections are new, and the weights and biases right associated with these connections has to be reinitialized. Either you can randomly reinitialize, or you can follow some reinitialization procedures which I mentioned. Now there is a question that whether, right? So what is the first step here? First step is to remove the top layer and insert a new layer, right? Remove the top layer, fine. And then insert a new layer, fine. Insert a new layer with only 5 number of neurons. And also we need to decide the same thing, that what kind of activation function should be associated with this layer. Let's say, for example, Softmax. Of course, Softmax, if you are solving a classification problem. Also cross entropy or categorical cross entropy we have mentioned, let's say, for example. And then you have to decide that how many only, whether you need to only fine tune the last layer, or you have to fine tune the whole layer, or you have to fine tune this many number of layers. That's what also you can decide. And you can also highlight the same thing in the code, whether you want to only fine tune this layer, or let's say this many number of layers, or fine tuning all the layers. And we have talked about the scenarios. I mean, when to apply which one. Right. And then if you want to fine tune it, then you can just fine tune in the similar process. I mean, it is like retraining or readjusting the weights. The weights has already been trained, but the weights, basically the early layer weights are like generic weights, right? So which can be applied directly on the medical imaging, but the specialized layers, right, which are very, very specific to the natural images, has to be modified. Right. So then what you have to do is then we need to also, right, fine tune all the layers, because the model has not seen the medical images. The weights have not been adjusted based on the medical images, because the target domain is completely different here, right? The target domain is completely different. So what you can do is we need to also fine tune all these layers. So you can also fine tune all the layers. Right. So you need to just write in the code that, or you need to mention in the code whether you need to fine tune all the layers, whether you need to fine tune few layers, whether you need to fine tune the last layer. You can also do the experiment with all these possibilities and check which one is giving, which one is performing well in most of the cases. That's what also you can do, right? Experimentally also, or empirically, you can also decide which one is good. Theoretically, we have seen which one is good, but empirically also you can decide which one is better, right? So similarly, in the unit architecture, I mean, coming to a segmentation task, right? Segmentation task is very, a little bit different, as I mentioned earlier. And as I mentioned, I mean, segmentation task, the encoder and decoder based architectures are more popular nowadays, like unit based architecture, where there is an input image, an output image over here, and here there are some blocks, basically, let's say convolutional blocks. Fine. Let's say these are some of the one block here, which contains 2 convolution block, and inside the convolution block there are some ReLU layers, maybe some variants of the ReLU. There are some you can say there are also some pooling layer followed by this. Let's say there is a pooling layer here to downsample the feature map from one size to another size. And there are some normalizations layers, which are also very, very important nowadays. So like batch normalization layer, right, has some of the importance in overcoming some of the problems. Here is something known as bottleneck layer, not necessarily required for all the architectures. And then the corresponding, right, the corresponding, you can say the decoder layers, and the size, right, should be same, so that I can take the output from the encoder to decoder and concatenate them together, and then finally process, right? And finally, I have to upsample the image here, either using transpose convolution, as I mentioned, or op convolution. If you want, you can also go for some interpolation techniques, but always learnable is better, right? This is learnable, right? So like we have used convolution here, but you have simply used a pooling operation. So but in the decoder, we are not using it. I mean, this kind of interpolation techniques, or you can say downsampling operation, sorry, upsampling operations. Instead of the traditional upsampling operations, we are using transpose convolution, right? And then finally, as I mentioned, so whatever the output you will get, here, fine. You have to also apply a 1x1 filter having C plus 1 number of times. I told you earlier, right? So why do we need? So let's say this is an image having size 256 cross 256. For simplicity, I have taken a grayscale image like an X-ray image, right? It's not a color image, so it's a grayscale image, and let's say the task is to classify every pixel either into class 1 or class 2 or the background. Background is very, very important here, right? So then what I have to do, as I mentioned, that see there are number of 2 classes plus 1 per background. So finally, I have to apply a 1x1 filter, which will not affect, right? Which will not have any effect or impact on the size of the output. So what I will ultimately get is having size, let's say 256 cross 256, and the depth will be 3. That means for every pixel, I will get 3 different values here. For every pixel, I will get 3 different values, right? And maybe the first value belongs to class 1, the second one belongs to class 2. And that means for every pixel, I'll get 3 probability values. And if I'll add them together, I'll get 1, right? Kind of softmax over each pixel rather than, right? Over each class, it is like softmax over each pixel. So for every pixel, you will get 3 probability value. Let's say for first pixel, you are getting, for past pixel, you are getting 0.75, 0. Let's say 2 and 0.05. This is what we have got for first pixel. What does it mean? The first pixel should belong to class 1. So accordingly, you will design another map here finally, and you will tell it belongs to class 1. This pixel will belong to class 1. Maybe you can, just represent this in 3 different colors, right? Maybe the background is black, or maybe this class 1 may be in yellow color, or maybe the second one is in green color, right? If there are only 2 classes, one is for tumor, one is for background, so black and white is okay. Class, and the black basically tells us the background, right? So similarly for the second pixel, you will get another 3 values, and again you will compute you will check the output. I mean the mask basically, right? You have to always look at the mask. If the mask says yes, it is class 1, then your probability, I mean your model is also giving it is class 1, then of course it is a correct classification. I mean, we're solving segmentation problem, but in the form of a classification task, right? So classification means here we are doing pixel level classification, which is a segmentation task. So for every pixel, what I'm trying to say here is for every pixel, you will get a loss, right? So then what you have to do, you have to add this loss of each of the pixels, right? So here also you are applying, let's say cross entropy loss, but it is the sum of the pixel wise cross entropy loss, not the exact cross entropy loss which we are discussing about. I mean, which you have seen in case of classification. There are different types of, other types of loss functions which we have known as dice loss, focal loss. There are different types of loss functions we have for this image segmentation task, right? So, but that is what we need to understand, that what do you mean by this cross entropy loss in this case, and how it is computed. Very, very interesting to understand that for every pixel we're getting probability values, and then based on the highest probability value, we are assigning a label to a particular pixel. I hope it is clear, and now we can directly move on to the demonstration part. Okay. So I could not see any other queries. Let us directly move on to the demonstration part. I will share the code with you. Don't worry, right? Whatever the code I'm having, I will share with you very soon, right? So I'll just quickly show you some of the codes which I have written using TensorFlow Keras, right? If you want, you can also use PyTorch for that. Two different ones, right? So as I mentioned that, so I have to initially, right? I'm using Google Colab here. You can use Kaggle. You can use whatever you want. If you want to locally do it, you can locally do it. So then just I'm just trying to import the libraries which are important for me. I have already mentioned that NumPy is very, very important. Matplotlib is important sometimes for plotting. And at the same time, TensorFlow, as I mentioned, TensorFlow Keras, import CV2, very, very important for manipulating the images. You know that. So I think, okay, I have taken one data set which I have already stored on the drive. Okay, it doesn't have any validation set. Okay, I have not taken validation, but if it is given or if you want, you can also, I mean, just for example, I have not taken here, but you can take if you want. So I have training set, I have testing set, and another, I mean, the most important thing which we always do, you can say the most important stage is always we need to have some augmentations, right? So I have also put some augmentations over the images and just simple augmentations like some transformations, affine transformations I have used. Then the images are already given in the form of a folder. So I'm just taking the images, directly reading the images from the folders, right? And also deciding the size, batch size, the target size, basically the image size, and training testing folders are already given to me, so no need to go for training testing divisions, right? So directly I'm loading those training testing samples. I'm in the training testing folders. And this is where actually I have designed a simple sequential CNN architectures having 3x3 filters, 32 3x3 filters with ReLU activation function, which is applied on an input having size 100x100x3. And then I've applied a pooling layer. See how easy it is to call a two-dimensional. I mean, we're not writing the code right from the scratch. We are just calling the function which is already available on the Keras. Right? So Keras is having a function called as convert2D, which takes different parameters. What are the parameters? Like 32 is basically tells us the number of filters you want to choose. Then the size of the filter, which is 3x3. It can be 5x5, 7x7. It can be 1x1 as well, right? It's up to you that how you are designing the model. And then I have just repeated those, the convolutional layers for a few times, and then followed by a flattened layer, because ultimately after this max pooling layer, I mean, this max pooling layer, what we are getting is a feature map having size 10x10x128, and the depth always depends upon the number of filters of the previous layer. So what we are getting is 10x10x128. There are various ways actually to process these feature maps through the classifiers, and the simplest way is flattening it. I mean, just by converting, it is a 3D matrix. So by converting this into a one-dimensional vector, right? Or else you can use global average pooling over here, which is a very common practice. So instead of, I mean, you will be having, after applying actually these 3x3 filters 128 times over here, right? And what you are getting is ultimately a feature map. I mean, 128 feature maps having size 10x10. Right. So then we're flattening it, passing it to some of the dense layers, not required all the time. You can see just for example, I have added here a dense layer. You can see the number of parameters involved in the convolutional layer is very small compared to the involvement in the dense layer. I already mentioned, right, that how many, I mean, this is a very simple architecture, and this total number of parameters, if you count here, it is around 1.7 million. And out of 1.7 million, more than 1.6 million parameters are only because of the dense layers, right? So that's why I told that we need to be very, very careful while choosing the dense layers, whether dense layers are really required us or not, right? And then what you have to do is you have to just choose I mean, basically you have to decide the hyperparameters. and then train the model using model.compile, model.fit, where you need to pass the type of optimizer you want to use, the type of loss function you want to use, or in the model.fit function. Basically, these are all the functions which are already available, right? It's just like, English kind of statement we are using here, right? And these are all functions. If you know how to use the functions, it takes a lot of parameters. You need to only pass the parameters, right? So see, in place of actually validation, I've just passed a test data, which is not actually correct, right? Because I don't have validation set, I've just passed it. But if you don't have actually validation set, you need not to provide the validation set during the training. So if you're only having training set, you can just provide here. I mean, sorry, validation set, right? So just for, just to show you something, I have just written here test set, but this should not be tested. This should be always validation, or you should not take it, right? So then you will just go for training the model. If you want, you can also see the graph of the training loss and the validation loss, training accuracy, validation loss. This is the convergence graph. The training progress, you can see whether the training is converged or not. If it is not converged, you have to run it for a few more epochs, train the model for a few more epochs, and then you can stop the training process. Then once the training process is stopped, you can just evaluate the model by providing the test set, right? So that's why actually, we need three different sets basically, as I told, just to see the progress, how it is progressing. We always need training, validation and all. And even during training also, you can pass the early stopping criteria. So when there will be some, there will be some increase, right, in the validation error. So you can just stop the training process. That's what also you can do. This is the first one, right? So here, if you want, you can also change your architecture, whatever you want, like the architecture which I have shown you. And this is the code. The codes are already available on GitHub, right? So this is one architecture which we designed. Already I have shown you that MFLnet, multi-scale feature learning. That this is for that we have just defined the MFL block, as I mentioned, right? Which is very, very important for extracting multi-scale features. We have just defined the MFL block over here, and MFL block needs some 3x3 filters, which I have already shown you. And this is, how actually we designed a mini block. This mini block is nothing but a simple 3x3 filter, right? So, and then this MFL block, basically, as I mentioned, the way we have, I have shown you that sometimes it needs concatenation, sometimes it needs additions, like the skip connections. That is what I have just written over here, nothing else. Nothing else. In one block, I have called a 3x3 filter, and another path 2 times 3x3, and the output of them are concatenated. That's what I've written over here. You see how easy it is to code your own model, right? Whatever is coming to your mind and whatever you have decided to implement. It's very easy. This is the final model where you can anytime, if you want, you can just call the blocks. So I always used to prefer writing the codes in the form of the functions, because you need not to write the same code, so many times, so that the code will look very bigger. So what I've done is I've just call a function over here. I've defined a function here, right? And just I'm calling the functions by providing different parameters to the function. That's it, right? And ultimately, if you look at, I've just instead of flattening, I told you that instead of flattening, you can just pass global average pooling over here, and finally we are having the final convolutional layer, final dense layer with activation function softmax, and the dense layer will have how many neurons? Number of classes, which is 2 here in our case. And then similarly, we are here passing the hyperparameter values, like the learning rate, the which type of optimizer function, which type of loss function, and so on. And here is the details. If you want, you can just summarize the model with the help of model.summary. Model is the parameter or the variable where I've stored the model. And dot summary will help us in summarizing the model in terms of the output size after each layer, as well as the number of learnable parameters required at each layer. Right? And then it is the whole training process. You can just see the growth, and then you can just get the output like this. Coming to the transfer learning part, in place of transfer learning, as I mentioned, I did not to design the model from the scratch. The other parts will remain same, right? How to divide the data set into training, testing, the augmentations like rotation, little bit of flipping, rescaling, zooming, flipping, or the vertical direction or horizontal direction, which one is useful for us. And then augmentation is done, and this is how actually augmentations looks like. Sometimes some augmentations are not useful, and you have to be very, very careful. And now this is the code. So what do you mean by transfer learning? We all know that, right? Let's say I want to use VGGNet to solve, let's say, this chest X-ray classification problem. How to solve this? Right. So as I mentioned, the weights is equal to ImageNet. What does it mean? VGGNet was designed on ImageNet datasets. So we are loading the same weights on which the on which the VGG16 was trained. That is the ImageNet weights. And then we are also passing one parameter over here known as include top is equal to false. So what does it mean? That means we want to remove the last layer. Right. So that means we don't want to include the top layer, which is the final classification layer, because we have to replace it with the number of classes which we have in our target task. Right. And at the same time, I'm also passing the input size. Right. So then, and then I'm storing with a different variable known as the base model. Then this base model dot output will give us the output just before the previous layer. The last convolutional layer, and we are just removing the top layers here, right? And then finally, I'm applying a global average pooling layer, and there is an additional, dense layer. If you want, you can add, and if you want, you can, you can just remove it, because we know that this may lead to some high computational complexity. So this is the 3-class classification problem. The final layer is a dense layer having 3 neurons, softmax function. That's it, only 3. And then one more thing you need to only mention, that whether you want to train the last layer or whether you want to fine tune the last layer or fine tune the whole model. So this is what is the code here, very simple code, right? With a layers trainable equal to false. If you want to train the layer, all the layers, then you have to write here yes. And if you want to freeze the layers of the pre-trained layer, then you have to write here false, right? Layers trainable false. That means we want to freeze the other layers. So if you write yes here, then you can fine tune all the layers, right? Fine. Again, the same things, whatever I've explained. Model.compile will help us in compiling the model. Model.filter will help us in training the model. You have to decide the number of epochs, as I mentioned earlier, right? And everything else, all the hyperparameters. And once it is trained, then you have to evaluate the model. You can evaluate the model. And this is our, I'm getting some of the results over here. So you can just design a model from the scratch, and you can also use one pre-trained model and check the performance. And if possible, it is always a good practice to also learn, or you can say design a model from the scratch by looking at some of the pre-trained models like VGGNet and all. So then then you will easily learn that how to design the model, right? So similarly for unit, for segmentation task also, you can directly, the codes are very simple. You'll be only having 2 parts. One is the encoder part, where as I mentioned that every encoder is having some blocks, and every block is having, let's say, 2 3 cross 3 convolutions, and along with convolutions you have to provide the activation functions, and whether the padding is same or padding is different. Usually we are choosing padding equal to same, means after even applying 3 cross 3 filter, you will get a same output, right? And then 2 times sequential 3 cross 3 convolution followed by max pooling. Again, the same procedure repeated for 4 different blocks, as I mentioned. And there is a bottleneck layer over here. And again, that in the decoder, as I mentioned, that yeah, we are using, you see here, the convolution transpose, right? So that means transpose convolution we are using, right? And that we need to also check, what should be the size of the filter and what should be the size of the stride to get back just the size, or the output size just is the double version of the input, right? And then as I mentioned, you see here the concatenations. What do you mean by concatenation? This is where actually we are, this is how actually the skip connections, although it was looking very different, right? So that time, but its implementation is very easy. So what we are actually doing, so we are trying to take the feature, output features from the encoder and concatenate with this output U6 here, right? So you can see C4, what is C4? Is just the corresponding, this is what this output of this block, right, is output of this block is basically taken, and here also we are applying a transpose convolution over here, and there is an output, and here is the output. So this size and this size has to be matched or else you cannot concatenate, right? It's just a concatenation of two matrices. It's very easy. And that's what we are doing over. See how easy it is to design the unit architecture, right? So then if you want, you can make also any changes, right? At every layer. And that's what people have done, right? If you just, instead of this C1 plus C2 is here, right? C1 plus C2, and there's a max pooling layer. There's a C1 layer, there's a convolutional layer, there's a, and let's say there is another convolution layer here, right? And you have got another output over here. And let's say you want to introduce a skip connection over here. What is skip connection, right? So skip connection is just you want to add the values of the previous layer, right? So that means, let's say this is C1, this is C2, and the input value is, let's say, C0. So what you will write over here is, so I mean, the final output will be equal to, let's say, C2 plus C0, right? That's the skip connection, and that will become a residual connection for you. And you will repeat the same thing for every block. So it will become a residual unit architecture. It's very simple to, code, because the functions are already available with us. Yeah. So here is some of the codes. Again, as I mentioned, at the final layer, I'll be having 1 cross 1, right? 1 cross 1 filter. How many times? It will be equal to number of classes, right? I mean, plus 1 basically I've already added into it, right? So, and it is basically, okay, I'm using, let's say, sigmoid. So for a 2-class classification, a 2-class segmentation problem, so it can be, if it is sigmoid, then you can just take 1. If you're taking softmax, then it will be number of classes plus 1. You know that. Right, and then the same procedures, right? I mean, for training and for testing, nothing is there. This is how actually it looks different from the traditional CNN architecture. And here only we are having 2 parts. One is encoder part, and another one is the decoder part, nothing else. And the same procedure you have to follow for training the model and testing the model. And here is also the same code in PyTorch, right? And because as I mentioned, that syntax will be different, but the concept will remain same. Only the syntax is different. The same architecture we have designed over here, right? So it's basically everything is designed with the help of a class. And the functions basically within the class, the same concept here. We have designed a block having two convolutional layers followed by pooling, 2 convolutional layer followed by pooling, and there are 4 encoder blocks, as I mentioned, 4 decoder blocks, and there is a bottleneck layer over here, right? And finally, there will be 1 cross 1 convolution layer, as I mentioned. And you can see we have just fine-tuned, we have trained the model on a data set called as retinal fundus imaging data set for vessel segmentations, retinal vessel segmentation. And here are some of the outputs. Let me show you some of the outputs I think I'm having. I'm not sure whether, yeah, there are some outputs as well. You can see the outputs. This is the input image. This is a retinal fundus image. I mean, we are having 2 lectures on this retinal fundus imaging and retinal OCT imaging. And this is the fundus image basically. And here are all the retinal vessels you can see in the ground truth. See how difficult it is, right? To annotate, the medical, basically the segmentation data set. It's very, very difficult. That's why I told that annotation is very intensive here. And that is the output which you have got from this model, right? See. And there are also different performance metrics. Accuracy cannot be considered as a performance metrics here because we don't believe in accuracy here. Accuracy means how many pixels are correctly classified out of all the pixels. So here, even if my model is not going to classify any of the white pixels and all the, let's say all pixels are black, still it would give me a very good accuracy. Why? Because all black pixels are correctly classified, right? So that's why accuracy and those type of metrics which we used for classification cannot be used here directly, right? So we have different types of performance metrics like dice coefficient, there is a Jaccard coefficient, or you can say right, other types of like intersection over union, right? So that those can be used here directly. And here are some of the other results you can see which we have obtained. Yeah, some interesting results which we have obtained using this simple traditional unit architectures, right? So there are some connections which are not proper. You can see over here. There are some connections. If you look at carefully, there are some connections, right, which is not clearly, right, which predicted by the model, and which you can predict with the help of some variants of the or advanced variants of the unit architectures, right? Yeah, so I will stop here because it's I think 8 p.m. So I'll stop here. If you're having any queries, so I'll be happy to take any questions. It is a, okay. This is a very good question. You can see in the chart box. So if the original image is of large size, then yes, resizing is one of the major limitations in convolutional neural network. If you are using, let's say, transfer learning, so most of the time we used to downsample the size to, let's say, 224 cross 224, because most of the architectures used to take this type of size, right? So I mean, but doing this right, this downsampling also leads to some information loss, right? So then then what to do, right? I mean how to resize, because we usually just apply the resize function which is available on the OpenCV, and we used to resize it. Then what is the best way to do this, right? How to solve this problem? So one of the ways to divide the image into different patches, and you can just take the patches to, there are patch based learning process or patch based architectures or deep learning architectures, and VIT is very very popular for that, like vision transformers, which is a patch based architecture. I mean the traditional VIT I'm talking about. And while also resizing or downsampling the images, what you can do is you can choose an appropriate approach to downsample, right? Because there are several approaches through which if you downsample, you may lose much information. So you need to be very, very careful while choosing the interpolation technique, and what kind of interpolation technique you should choose. Like bicubic interpolation technique is one of the most popular interpolation technique compared to the nearest neighbor, right? So because if you use nearest neighbor, so you will lose some of the information, and again it may also leads to some of the artifacts which is not required, right? And for which even CNN may learn some I mean irrelevant things, or um, so that's why we need to be very very careful. And patch based learning is one of the solution where you can divide the images into certain patches, and then you can solve the problem. Okay. And any book research you could suggest that could help explore, understand programming kind of thing. Okay. Programming, I have seen there are few books where they have mentioned that I've not gone through those books, that implementation of convolutional neural network deep learning architectures using Python or Keras or TensorFlow. There are some books available, but you can also search, some of the what I can say blogs or GitHub pages, right, provided by some of the researchers. If possible, I will also share some of the resources. I mean, at the end of this FDP, I mean, which are required to at least get some codes. I mean, which are what actually reliable source, right? Which is very very important for us. Okay. Any other? Mm, oh, not so many. Sir, my data set has no ground truth. How can we proceed? Oh, very difficult. Very, very difficult. You cannot directly use then any of the, what I can say, you can any of the supervised techniques directly, right? Or else, as I mentioned, that you can just take the help of the foundation models, like if you are dealing with segmentation, like foundation models like SAM, segment anything model, is very very powerful model, right? So you can just there is a made SAM model also available. You may just take help from those type of architectures, like how to adapt or how to adapt those type of foundation models directly if you are not having uh, labels, right? But label is good always, right? So that you can at least fine tune your model to some extent, right? So at least you need a few of the labeled images, right? Not more, but few of the labeled images are required. Resources, especially for medical image processing, difficult. So very very difficult. Medical image processing, maybe you will get some of the books available, but those are traditional medical image processing. I don't know whether you would like it or not, because those are all like where you will find that most of the image, I mean, low-level image processing algorithms were applied to solve medical imaging tasks like age detection, noise removal, medical image enhancement, probably. I mean, you may not like, I mean, particularly in this time. Why? Because there is a very, I mean, they have not